Section 6.6 is proportions and variation. So let's start looking at an example. I drive at an average speed of 60 miles per hour. Let's fill in the chart below based on the different hours I've given you. So if I go for 1 hour, I go 60 miles. If I go for 2 hours, I would go 60 and then 60 again, that's 120. If I go for 3 hours, I go 60, another 60, another 60, so that's 180. And if I go for 4 hours, I go another 60 miles, so that gives me 240 miles that I go. This idea that we're looking at here, where each hour that goes by, I go another 60 miles, so for each hour, I gain 60 miles. We could actually come up with an equation for this. We've looked at this before. The 1 hour is 60 miles, 2 hours is 120 miles, and so forth. So t hours will be whatever miles per hour I went, 60 times the time, which will give me the distance. So the distance is equal to 60 miles per hour for each hour t that I go, and this idea actually leads us to the concept of direct variation. And loosely speaking, it basically says as t goes up, the distance goes up also, but we have to be specific and define exactly how it is that d goes up when t goes up. Notice every time t goes up by 1 hour, d goes up by exactly 60 miles. So what is direct variation formally? Direct variation says that y varies directly as x, so the first variable varies directly as the second variable if y equals kx gets satisfied, whereas k is known as the constant of proportionality or constant of variation. So if we go back and look at our problem here, we could say that d varies based on this idea. We can say d varies directly as t, with k in this case being 60. So it basically says that as t goes up by 1 unit each time, d goes up by 60 units each time. And also, if you can remember from before, it's really a linear relationship, y equals mx plus b, where in this case y is d, m is the slope, 60, x is the t, and notice how the b or the y-intercept is 0. So any linear relationship with a y-intercept of 0 is really a direct variation situation. Now another thing I want you guys to remember from this is that if I divide both sides of this equation by x, I always get y over x's k. In other words, if you're looking at a table of values, you can tell if they vary directly by looking at the quotient of each of the successive values. So for example here, 60 divided by 1 is 60, that's your k. Here, 120 divided by 2 is 60, that's your k again. Here, 180 divided by 3 is 60, that's your k again. And then 240 divided by 4 is 60, and that's your k again. So when you look at the values, the quotient of y over x, they always give you the same constant of proportionality. So these are just some of the things you want to keep in mind. Direct variation is y equals kx. You can easily look at a set of data and tell whether they're directly related or not. Again, the other thing to keep in mind is that since direct variation describes a linear model, y equals kx, the data will always graph into a line with y-intercept 0. So when I look at data that are linearly related, the data are going to line up in a linear manner going through the origin with a y-intercept of 0. Let's look at an example. It says, does the data represent direct variation? And if yes, find k. So So if the data is to represent direct variation, it must fit y equals kx, or the quotient of y and x must always be equal to k. So that might be a quick way to go check the data. Let's see, here's y, here's x. 6 divided by 1 is 6. Then I have y and x. 30 divided by 5 is 6. That's already looking good. 54 divided by 9. So their ratio, notice, is always the same number. 59 divided by, or 54 divided by 9 is also 6. And then the last number, actually I have it wrong, I believe. The last number really should be 90, if I've copied the example correctly. Then I have 90 divided by 15, which is also equal to 6. So this, right here, looking at the ratios, I always get the same constant of proportionality, k. So our answer for this would be yes, their ratio is always k, which in this case is 6. So y equals kx. In this case would be y equals 6x. That would be our equation, and k would be equal to 6. They didn't ask for the equation, they just asked for the k value, which we found. So notice if I go to just some random set of data, if x is 9 and I multiply 9 by 6, I do get 54. So that set of data gets satisfied, and if I go to all the data points, they will all get satisfied by that equation. So k in this case is 6. So we looked at direct variation and the idea of it. Let's look at another example. I have to cover 100 miles and I drive at different rates or average speeds. Fill in the table based on that idea. So if I'm going at 10 miles per hour, how long does it take me to get to my destination? Well, 100 miles, I'm going at 10 miles per hour, it must take me 10 hours to get there, so that rate times time can give me the 100 miles I'm covering. What if I double my speed and go at 20 miles per hour? Well, if I go at 20 miles per hour, each hour gets covered 20 miles, so to cover the 100 miles for my destination, I must drive for 5 hours, so that 5 times 20 can give me my 100 miles. Now what about if I go at 40 miles per hour? Well, 40 and 40 will give me 80, and then that'll leave me another 20 miles to cover, so that'll take me another half hour, because each hour I'm going 40. That would be 2.5 hours to get me to my destination, so that their product could give me the 100 miles. Now if I go really fast at 80 miles per hour, in 1 hour I've already covered 80 miles, and then I'll need maybe a fourth of the other hour to cover the other 100 miles I have left. So it really requires me to go for an hour and maybe a quarter of an hour, another 15 minutes to be able to cover the 100 miles. Now notice, as r, or my speed, keeps going up, my t, or time, keeps going down. So this idea kind of leads us to the idea of inverse variation, which loosely speaking tells us as one goes up, as one variable goes up, other goes down. So that's very, very loosely speaking again. We haven't really defined it of exactly what it says. Inverse variation acts in an inverse manner, as you might imagine. One goes up, the other one goes down. So what does inverse variation say? Inverse variation says y varies inversely as x if y equals k over x, where k is the constant of proportionality or variation. Kind of like we did for direct variation, but direct variation said y is equal to a constant multiple of x. So you multiply x by the same constant to get your y. In other words, y kind of gets blown up and bigger and bigger and bigger because k is always a non-zero constant. Now, this guy over here, inverse variation, says as x gets bigger and bigger, you keep dividing the same constant by x, so naturally y gets smaller and smaller. Notice here, r got bigger and bigger and t got smaller and smaller because you were taking the same constant and dividing it by bigger and bigger numbers. So let's go back and analyze one other thing. Let me point out. Notice if I multiply both sides of this equation by x is the lowest common multiple, I'm going to get yx is equal to k. So inverse variation also says that the product of your two variables will always be the same exact constant. Now let's go over here. If we want to analyze, let's get rid of these guys. This example we looked at, we have 100 miles that's fixed, and each time I'm dividing the 100 miles by the rate, to get the time accordingly. So in other words, to get the time, I always said, well, I go the 100 miles, then I divided by the speed, which is 10, that gives me this guy. Or here, for the time, I said, I go the 100 miles, but now I'm going at 20 miles per hour, so that's going to give me the time, which is 5 hours. Or in this case, I said 100 divided by 40, which gave me the time. In this last one, I said 100 divided by the 80, the fast speed I'm going, to get the 1.25. So to get the time, I was just taking the distance and dividing it by the rate, of course. And my distance was fixed at 100 miles. So 100 divided by r gave me the equation for this scenario. In other words, t varies inversely as r, we can say in this case. So that as r goes up, t gets reduced. And my constant of proportionality in this case was really the 100 distance I was going. I can also check that by this idea we mentioned, that the product of the two variables will always be the same constant. Notice 10 times 10 is 100, 20 times 5 is 100, 40 times 2.5 is 100, and again 80 times 1.25 is 100. So anytime I multiply the two values of my data points, I'm going to get the same constant of proportionality, 100. Another thing to point out is that as x goes up and y goes down in an inverse relation, and not in a linear manner, because notice I don't have y equals mx plus b of any form, I have k divided by x, so there's actually a division going on, and this is actually a rational function because there's division by a variable. The graph of inversely related data will look like a set of data points that are obviously decreasing because as x goes up, y goes down, and it'll look somewhat curvy. So keep that in mind. If I were to connect the dots, it would look curvy and not linear. In other words, if I go graph these data points right here, it's not that if I go up by 10 units in my rate, my time will go up by 5 hours consistently. Notice from here to here, it's not going down by 5. When I'm doubling the speed, it's going down by 2.5, which is actually half of the previous one. So for that reason, I'm not going to have a linear relationship. I'm going to have a rational curve, which is actually not again linear, and it's going to look curvy but decreasing. Let's look at an example. Is the data inversely related? If yes, find k. Well, it must fit y equals k divided by x, or yx equals k if it is supposed to be inversely related. Also notice as x goes up, y goes down in this case. So because x goes up and y goes down, I'm thinking, yeah, maybe it does fit this, but I have to go test it. And when I do that, notice the product of each of the x's and y's always gives me the same constant 210 as this would indicate. So I'm thinking, yes, y is equal to k over x with k equals the same 210 I always get. So y equals 210 over x, and if I go check any of these, like let's say this one, 210 divided by 10 does give me 21, and it gets satisfied. So I got the equation and I got the constant of proportionality.